Alright, today we are doing 1.7, which is piecewise functions. So the key vocab, guys, what did I just say? Focus. I don't want to have to remind you guys every time I take a breath to not talk. Okay, so a piecewise function is a function that is written using two or more expressions. A reminder is to indicate that the endpoint is not always included in the set, so sometimes we have to use parentheses, okay, if there's an open circle. That's the main idea here. And a bracket is used to indicate the solution does exist at that point. So we're just going to evaluate piecewise functions to start before we start graphing them. Step one is to identify the function in use. So for A, does everybody see why we're using f of x? Because the function given is f. Okay, so that's the function we're going to use. Now step two is determine what we're evaluating f of. We're evaluating f at an x value of 2, correct? So, with that being said, we're going to look at which one of these boundaries or intervals bounds 2 falls in. Is 2 less than or equal to 0, or is 2 greater than 0? So, for that reason, we're using this boundary, which means our answer to this question is 2. Okay? If our value had been less than 0, less than or equal to 0, it would have been 3. Okay, we're going to do more examples of this, so if it's not clicking or sticking, you're going to see it again. Alright, next one we're going to use g of x. So for g of x, we're looking at the x value of 7. Is 7 less than or equal to 3? Or is 7 greater than 3? Greater than 3, so we're going to use this one. Now the problem with this is there's an x in it, so I need to plug what in for x? 7. Which gives me 13. Okay? Now we're going to try it again with the h of x. Okay? So for this one, -4, does it fall in the first or second interval? The first, because -4 is less than or equal to 2, right? So I take the function at that piece and I plug in -4. I get -2 minus 4, which is -6. So you just find, evaluate, okay? Now a lot of people get confused when there's just a number there instead of an x. When it's just a number, you just take whatever that number is. That's what we call a constant function. It's horizontal, okay? Now for the next one, g of 0. Is 0 less than or equal to 3 or greater than 3? So we do 0 plus 5, which is 5. So that's pretty straightforward, pretty easy. That's how you evaluate a piecewise function. Okay, that's how you evaluate a piecewise function. Now, we're going to go into the graphs of piecewise functions. So, stage 1, we're going to just start by identifying the domain and the range of the piecewise functions. So domain is all the possible x that this function will take on. I'm going to show you how to do this algebraically and visually, okay? So on this particular one, x is less than -2, -1, or x is greater than or equal to -1. With these two intervals in place, do we take on every x? Do we consider every x? Do we leave anything out? Well, we go from all the values that are less than -1, and then we pick up at -1, and we start up again at the values that are greater than -1. So is anything left out in the x's? No. So it's going to take on every single x. Now visually, how does this look? I'll explain. Visually, for the domain, when one function picks up, the other one has to leave off on the same x. Do you see how here, even though there's a vertical gap between the two functions, do you see how if one function has an open circle, the other one picks up at the same x value? Do you all see what I mean by that? If that happens everywhere, that function has all real numbers, -infinity to +infinity domain. Now we're going to talk about the range. The range is a little bit harder to identify. So as for the range, we're going to look at each piece separately. Does this function go down forever? It goes down forever, but then it stops going down at what value right here? -3. Does it actually take on -3? So I use a curved bracket. But we have a problem. We have this other piece of the function up here. So here's how we do that. We have a range for this one. We already identified that, right? Now what you're going to do is you use this thing called a union symbol, okay? And now we do the range for the other piece of the function. It's more like a U. It's kind of like a hybrid between a U and a V. So as for the symbol, we go from 2 to positive infinity on this one right here. You guys all see that? And why did I use a bracket instead of parenthesis on that one? Very good. So this is what we call a range gap. I'm going to show you what that looks like. So you see this whole section right here where all those y values are never being taken on by the function. So any y between -3 and 2, or less than 2, those are not being taken on by the function, which is why I need that union symbol. Does that make a little more sense now that you've seen it that way? Okay. Now for the next one, you see how every one of these intervals picks up where the other one leaves off? And you see how if we go across, every single time we have an open circle and a closed circle, they always line up with each other? Everybody see that? So it picks up where the other one leaves off. So there's no holes in the domain. And another quick question for you guys, just something to think about. Would this function pass the vertical line test, or this relation rather? Who says yes? Okay, who says no? All right, let's think about it for a second. So, if we were to draw a vertical line, maybe like right here, I'm thinking this is where you guys think it's a no. If I drew a vertical line here, how many points on the function do we actually touch?
One, because it's the open circle.
Good. Think of it as this way. The vertical line's going right through that open circle. It's not actually touching it. So this still passes the vertical line test. If this had been a filled in circle, then you would be right. It wouldn't. But since it's open, it's still a function. Okay, does that make sense to everyone? I just want to make sure you're aware of that. All right. Sure.
How do we handle it if they're both closed? Or they're both open?
You won't see something like that too much in this class, if that makes you feel any better. But if that's the case, in terms of your domain, it can't affect your domain. You'd have to do a split domain like the range. But that's more advanced, to be honest with you. No. If we do, we'll have a whole lesson on it. Like, it's a whole other thing. Don't worry. So as for the range, let's look and see if there's any gaps. As long as one function takes on all those values, we don't have to worry about the other pieces of the function, right? So what's the lowest this function ever goes?
0.
And it goes up to positive infinity. Do you see how this function alone, this piece of the function alone, takes care of any possible gaps? I don't even have to worry about the other ones. Now, of course, this one also goes to positive infinity, but because one of them is going to end up taking on all these y's, I don't have any gaps in my range, because at least one of the pieces takes care of all those empty pieces, right? All right, so now we're going to get into graphing. So I need you guys to have your attention and patience with me on this, okay? So go into it. I also need to make sure, and I recommend you guys are using pencil. If you don't have a pencil, try to use a pencil. Because there's going to be sections of this where I'm going to draw it and erase it for the purpose of your understanding. Okay, so step 1. What you're going to do is you're going to look at whatever the first piece is, x plus 3. You're going to take that and set it equal to f of x. So f of x equals x plus 3. Now if I simply just ask you to graph this right now, what would you do? You'd start at the y-intercept at 3, and then you'd go up 1, over 1, because that's your slope. So you'd all graph a line that looks something like this, right? That would be step 1. Okay. But there's one little difference to this particular graph. This graph only exists for x values that are less than or equal to 0. So this graph only exists in the part of the graph that's less than or equal to 0, only in this blue section. You all see that? Only in this blue section. Okay. So because of that, anything you graphed outside of that blue section is going to be erased. It doesn't exist on this particular graph. Okay? So that's piece 1. Now we're going to move on to piece 2. Now we do something where we basically mock graph. We kind of like pretend we're graphing at a certain area just to see where it would go if it existed there, just to help us progress our graph. So for the next one, we're going to do the same procedure. Y equals 2x. If you were to just graph this on a normal day, where would you start? At 0, right? Because the origin, because of the y-intercept, correct? But there's one problem. Its x is greater than 0, so does it actually exist at 0? So what kind of circle do I need to put here? Good. And then from there, it's always greater than, so all those values greater than 0 do exist. So I go up 2 over 1. I use my slope. Up 2 over 1. And you see how that open circle picks up where my closed circle leaves off right here? That's what you want it to look like. They're going to pick up where the other one leaves off. Yes.
Why is it closed again? I'm sorry.
You mean open?
Open, yeah.
Because there's no equal sign under the inequality.
Okay.
When there's an equal sign under the inequality, the end point where it starts is going to be closed, and then vice versa. All right. So since we picked up where the other one left off, we have a domain of. Good. And then what do you think the range is here? Do we have any gaps in our range? No, we actually don't, because technically this is taking on that 1, 2, 3 section. This is taking on everything. So it's actually just all real numbers. There's no gap in that range. There's no vertical gap. All right, you guys with me so far?
Yes.
All right. We're going to do a 3-piecer together before you do one on your own. So, we're going to start. I'm going to show you how to do this with erasing, and then I'm going to show you how to do it with mock graphing. So, whatever you find easier, whatever works for you, I want you to go with that method. So, step 1. We're going to basically graph this function, and I know it only exists where x is less than 0. So right off the bat, I know I need to graph my y-intercept at 1, but what kind of circle is this going to be? Open. Good. Now normally you would go to the right if you were just graphing this on a normal day, but it doesn't even exist over here. So I want to see where it would go if it went this way. So technically it would look like this if it were a regular graph, right? Which means the other side of the graph would look like this. Now which piece of this graph am I going to erase, the left or the right? The right, because it only exists when x is less than 0. So if it helps, you want to do these highlighted portions, and if it helps you visualize what's happening, feel free to do that. So it only exists over here. Alright, remember every linear function goes on in both directions forever, so that's that. Now as for the other piece, it exists between 0 and 2. So I plot my intercept. Now what's going to happen is you see how my other point overlaps my open circle? Do you guys see what I'm talking about right here?
Yeah.
Okay, because my intercept's the same on this one, right? And this one actually exists at 0 because of the line under the equal sign. And then it goes down 1 over 1, down 1 over 1. And then why did I stop there?
Because it ends at 2.
It ends at 2. It only goes from 0 to 2. Both are closed circles. Okay, like I said, this is going to take some practice to get used to doing. All right, and then the last piece, here's where mock graphing is going to come in. Normally you start graphing a line by graphing its y-intercept, but what's the problem with this situation?
Y-intercept's negative.
The y-intercept isn't part of my interval, is it? So here's where the mock graphing can help you. So I know that this piece is right here, this piece is here. If this helps you visualize it, go ahead and do that. So that's over here. Okay. So what I'm going to do is I'm going to pretend like I'm graphing it like a normal function. I start at -1, but I'm not actually going to graph it here because it doesn't exist here. It only exists in the yellow region, right? So I would technically go up 1 over 1, up 1 over 1, and now it starts existing, but it starts at an open circle. Then I do it again, and it actually exists here. So that's mock graphing. It's where you use the information about the whole graph to get information about the pieces of the graph. Does everybody see what I'm saying by that?
Yep.
Okay, so I pretended I started here, but I didn't actually plot it because it didn't exist yet. What do you think the domain is? Good. Are there any gaps in the range? No. No gaps. Okay. Lastly, this question, we are going to find the intervals only. So, see how they give us a piecewise graph and they give us the equations, but we need to come up with the intervals. So, firstly, I see this one here. I'm going to start here also because what do you notice this graph has? It has a y. It has an intact like y-intercept that's actually on the graph, right? And what is that y-intercept? 3. So I know that it's this one. Does everybody see how I was able to tell that it's that one? So with that being said, I can tell where that interval falls.
Less than 1.
Very good, less than 1. Good job. So x is less than 1 is the first one. I'm going to write it too. I'm just trying to get the colors good first. So yeah, this one is x is less than 1. Now as for the middle one is bound between what two x values? 1 and 2. And why did I use an equal sign under both inequalities here? Both circles are closed. And then what's the last one going to be? X is greater than 2. Strictly greater because it's an open circle. Now this is the graph that everybody kind of forgets about. Anytime you have just a regular number with no x, that's always a horizontal line at the value, the y value of whatever that is. You see that? Alright, that's all I have. I'm going to give you your homework.